This media was gratuitously produced by Clear Contributions Audio Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
Okay. As most of you know, I live practically across the street, so even if it's snowing outside and it's too bad to travel, I hitch the cats up to a sleigh and I'm here. Sorry. The other downside for you is I was born and raised in Michigan, so this is just whatever. Stinks to be you. All right. Since we're getting started a little later than I would have liked, and I would like to cover the last topic for this chapter, Diels-Alder reactions, we'll just go over your homework assignment real quickly with me just telling you what the answers are, and then you can ask me questions. We're not going to worry about stability of one form versus another, really, just because there are competing stability factors. It depends on the temperature and the compound and everything. So I just want to make sure that you can come up with the enol structures. So for B on page 11, I think, the one enol structure would be like this, where that's a single bond now, magically. And then your other, I shouldn't have erased that. Your other would be like that. You'd have two, since there are two alpha carbons. And of course, you get rid of one of the hydrogens. Forgot to mention that little point and put it up here. Okay, for this one, same issue. You'd have this as one of your compounds. And this one, it will be kind of easy to tell you which one is major. This is your other compound. The keto is more likely to be stable, and the enols would be equal to each other because they have the same number of allylic carbons. But anyway, those are your two products. Did you get those two products? Good. This one is a symmetrical molecule, so you only have to draw one of them. But you'd have this, and when the hydrogen disappears, you don't even notice it, huh?
You don't have to draw both sides.
No, because it's the same molecule, just flipped around. All right? Yep.
So this one, where you want us to draw where electrons are going, or just draw they were?
Draw what they were. Okay. All right, I want to get on to Diels-Alder reactions. These are kind of mind-blown kind of reactions. Just what did you just do? So it's going to take a little bit of work. And the good news, though, is I found that even as much as students are frustrated when I'm showing them how to draw them, once it clicks and the light bulb goes on, it's like it becomes their favorite reaction. I don't know if it's because you feel like you accomplished something or what, or the fact that you start with two molecules and you come up with a ring. But anyway, hang on through the frustration because you might find that you really like these. The biggest issue I have probably, though, to work with you on is how do you recognize that a Diels-Alder reaction will occur? Because a standardized test won't draw the molecules out in a tip-off kind of way. They're just going to draw a diene for you and another molecule that has a double bond, and then that's going to be pretty much the only reactants in there, and you're going to look at it and go, what am I supposed to do with that? So anyway, what you're looking for is a diene, which means two enes, and you want them to be conjugated, and they could have anything attached to them from there. I have a student one time who got me a t-shirt, and I have to try and find my t-shirt. It's like this. And it says, "Help me, I'm dying." Yeah, great. All right, then you're going to have a second molecule in there, probably different, and it will have a double bond with stuff attached, or a triple bond like that, and it could be either one of those with the diene. This is called the dienophile because it loves a diene. And you're going to create a cyclic compound by putting those two together. This is going to rely a bit on carbanion creation and resonance. That's right. That's why you have to have the diene, because you have to have a resonance system to be able to work with it. There are multiple ways that you can react the diene with the dienophile, because, for instance, usually these aren't symmetrical molecules. The diene isn't symmetrical, and the dienophile usually isn't symmetrical. So because of that, there's multiple ways you can orient them to close a ring. And as always in this class, we're looking for the major product. So I want to show you just the way that I'm always going to draw it to come up with a major product. There's a couple of different ways you can do it, but for consistency, I'm going to do it always this way. And so maybe you want to just kind of get in a pattern as well. What's going to happen during this reaction is that because of resonance, the dienophile is going to have electrons pulled away from a particular carbon. So you can see that the oxygen is electron withdrawing, so it's going to be pulling these pi bond electrons towards it, and if it does, then that carbon's going to be electron deficient. So then you can use these electrons to move them up there, and then that carbon's going to be electron deficient. Okay? If that's electron deficient and you have two pi bonds here and that's super electron rich, then the deal is you are going to use a pi bond to open it up to the electron deficient carbon here. When you do that, I know, nothing up my sleeve, we got everything electron deficient here. When you do that, and you pull these electrons away, you create a carbocation here. But you have a carbocation with a double bond, so you've got resonance going on. So then this is going to move down to here, and you create the carbocation up here. So the diene, you want to arrange it so that you get the best carbocation on this one and this one. So look at the carbocation combinations just like before. For instance, if I added to this edge of the resonance box, I've got a tertiary and primary carbocation. If I add to this edge of the resonance box, I'll have a secondary and primary carbocation. Okay, so it's the same thing as before. Box in the area, look at your combinations, pick the best one. And once you've picked the best one, I'm going to orient it so that this pi bond, where you're adding onto here, is at the bottom. So I've got where you're adding at the bottom and the carbon that you're adding to at the bottom, which, if you're lost with how you figure out which carbon here, you put the electron withdrawing thing at the top. Where you're adding for the diene at the bottom, the electron withdrawing group on the dienophile at the top. Any questions you want to ask me? Besides, why? Why? All right. So then, Here we go with the arrows, so you can see what we've got. What's gonna form as the product. So you've got chiral resonance system here, double bond, double bond. We're gonna move the electrons up from this. Electron direct thing at the top, tertiary, primary. This pi bond is electron rich, that's electron deficient. So the first thing I'm gonna do is move the pi bond over.
So what gives the, I guess, like, why does it loosen that pi bond and go over there? Why wouldn't it just stay the way it is right now?
Because you have something electron rich and something electron deficient in the solution. So anytime you have that situation, there's a probability for a reaction to try and stabilize, each situation. Okay, if you do that, you're going to create a carbocation here. So we can do this in steps if you want to, but it's probably going to work easiest for you just to do it all as one thing. Okay, so if I bring these electrons down, then that's going to create a double bond here, right? And now this is where the carbocation is. When you added this bond to this carbon, it had to let go. Otherwise it has too many bonds, so it let go of the pi bond carbon and it came up to this carbon here. The reason that it's stable is because you actually have it resonating through here. So you actually have resonance contributors. But like I said, instead of drawing the resonance contributors, what might just be easiest is for you to picture like what electrons are going where, why. So if you had let go of this bond, so that now you have a single bond here. Then this is electron rich. The CH2 with the number 4 by it is electron deficient. So I let go of these electrons to here. Or if you want to, you can draw that as one arrow. I see that usually in textbooks where you're drawing one arrow from that carbon highlighted in blue to the CH2 instead of 2 steps like that. All right, here's your product. Starting with this CH2 group here. I've let go of this, so now this is a single bond here and it's become a double bond here. So CH2 coming down to the CH double bond. You've got the carbon with a CH3 group off of it. Comes down to the CH2. I've opened up the double bond to form a new bond of the CH. That's going to be the bond right here. This bond flopped over and now it's here. And I will color code this for you too. That's probably the deal. No, that's not exactly what I wanted to do. Okay. Can you even see the green? I can't see it from this angle.
You can kind of see that.
Yeah.
This pair of electrons is now here. This pair of electrons is here. And these pi bond electrons, I didn't have a color for them, so I made them blue just to match this. Those are there. Okay, you need a lot more practice. Before we launch into things like stereochemistry and such, so just a minute. Blah, 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 blah. There we are, page 21. I'll work through this with you, but not give you quite as much coaching ahead of time. So to react 2-methylhexyl-1,3-diene. And don't worry about the E or Z isomer or whatever, but you can react it with this. Those are the two components. And that's what I'm telling you. This is going to be really hard to like look at it and go, oh, I'm making a cyclic compound with this. You're watching for a diene and some random mysterious other molecule with double bond or triple bond. Okay, so your first task is to orient each one so that you've got the diene on the left like this, and then the dienophile on the right. So figure out within this section right here, which way do you want to flip it? Do you want to flip it so the CH2, CH3 group is coming from the top or on the bottom? So first figure that out the best you can, and then we'll talk about that.
Must be solving it or just figuring out which one is on top, which one is bottom.
Yeah, you figure out which one is on top and bottom. I'm going to let you think about it for a minute.
Oh.
May not look like it right off, but this is the same analysis pattern as before. You're looking for things like resonance, primary, secondary, tertiary, nonbond electron pairs, the stabilization features, and then you're also labeling any reactive features. The reactive features on this are going to seem a little bit less obvious to you, but you do have electron-rich pi bonds, and you do have a resonance area. So you're working with that. In addition, because you have the nitrogen on the other molecule, in addition to a resonance box there, that is coming all the way through here. There you go. Those are all the different features you're thinking about. The reason, though, that we're not going to be reacting, the reason we're not going to be reacting with the pi bond between the carbon and the nitrogen is because then you would have a carbocation on a carbon that is right next to something electron withdrawing. And in addition, we don't have any really good way of working with it because otherwise you would form a smaller ring. And we want to form a 6-membered ring. So that's why. All right, so because you have the diene, then you want to look, you want to decide which edge do I want to add onto. So if you add to this edge, then you have a carbocation on a tertiary. And then you also have a carbocation on a secondary. Whereas if you add to this edge, you'd have a carbocation on a secondary and then a carbocation on a primary. So I want to work with this set there. And I'm sorry, I'm writing into the margins, or I'm sorry, into the text. Can you see it okay?
Yeah, so that means the CH2 goes on the bottom.
That's right. So you want to make this side the bottom, and this is the top.
So why that side becomes the bottom? Or you just why you chose it because of the tertiary and the secondary. Why it's the bottom?
Because if you orient it like this, your carbocation is going to be here and here, the way that I'm drawing them all the time. So I'm putting the edge that I want to add to in the bottom so that when this bond opens up, I've got a tertiary carbocation that resonates down to, and then gives you a secondary. Like I said, there's different ways you could draw it. This is just the system that I'm going to do it as, and so I will always put where I'm adding at the bottom, just to make it consistent, to give the best carbocations. I have this thing today that I'm writing way too far into the text. I'm sorry about that. Here, I repent. There you go. Then the dienophile, I want to put the electron withdrawing nitrogen at the top. anything for you? Instead of words out in the air. Well, I'll put where I'm going to add the diene at the bottom. In other words, this interpretation up here, put that at the bottom. Put the electron withdrawing group of the dienophile on top. It'll be nitrogen or oxygen generally. What questions do you have for me? I'm seeing a lot of blank looks. Uh-huh.
In selecting the electron withdrawing group, what is it that you're specifically looking for?
Generally nitrogen or oxygen.
Those are like two.
Then you could have two possibilities. So if the molecule is symmetrical, then it doesn't matter which way you orient it. And if it isn't symmetrical, you got two products. That I'm hopefully not going to do that to you. Question. Once you've got it in this arrangement, then this is your electron with deficient carbon. So the pi bond opens up to react with that, which means that you're going to create a carbocation on this tertiary carbon. But you can resonate. Take these electrons and move them down, which means that you have a carbocation up here now. So you can take these electrons that you can either draw them going up to the, you can draw them going up to this carbon and then from there over to here, or you can do it directly. I don't care which one. But anyway, since that's electron deficient, you're going to be using electrons here to close the ring. Uh-huh.
The carbon in blue is deficient because of like a delta positive or
Yeah. So, and the reason why it has that is this is electron withdrawing. So it's pulling electrons from this carbon directly. But then also, if it pulls this pi bond electron to this, you've got a little bit of a positive here, then you've got resonance, and so you can move the electrons up here, and that's creating an electron deficiency there as well.
okay.
Okay, all right, so now we've got the arrows and all of that. There's no resonance stabilized carbocation. We don't have additional blah, 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 really. So we'll just cut to the chase and we'll do your final product. Just so you can picture where everything went. Oops, that's not what I wanted to do.
Isn't there one more methyl group on it?
Maybe.
Just
Where?
on the
Oh,
carbon
where?
below, the one attached to the nitrogen. So you drew a resonance bond. There should be one more methyl group off of that. The carbon you attached to from your dienophile.
Yeah.
Oh, I see, yeah.
Unchanged.
Yep, nope, I'm glad you did. There's a CH3 here, is what you're saying, so. Yep, You're right.
Yeah.
You're still looking incredibly iffy to me, so let's see, can you do the next one? Yes, you can. Page 23. I'm going to make you do this until you stop giving me the look. Yes. 1, 2. Oh. Welcome. Mm-hmm.
So here's my question: how is that carbon? So is that? No. Why are we reacting with the carbon? It has 3 bonds and a hydrogen, meaning it's stable.
Mm-hmm.
Why are we reacting with it?
It's stable, but the oxygen that you have up here is electron withdrawing. So you know how before we were labeling partial positives and negatives based on difference in electronegativity? So this oxygen is pulling electrons from this carbon. So this has a partial positive. So it's a little bit electron deficient. And then though, because it's right next door to pi bonds, you also have some resonance going on here. You've got pi bond. So in addition to have the oxygen as electron withdrawing, you can also pull electrons through resonance. And so there's going to be a couple of carbons that are electron deficient. You're reacting with this carbon down here though, because it's going to close into a 6-membered ring. So. Is it getting any better?
Yeah.
We're going to practice and practice and practice, but this is all of the material for the chapter for the first test. So you just have to be able to tell me when you might see a carbanion, be able to do stuff with an acidic alpha hydrogen, do ketoenol tautomers, and be able to draw the Diels-Alder molecules. So it's a pretty good bite-sized chunk, I think. I guess since we have 3 more minutes, I will show you some of the finer details of what you need for the diene and dienophile. I'm on page 13. Not all dienes can participate in a Diels-Alder reaction. Some dienes are also going to be better than others. Some dienophiles are going to be better than others. So we're going to sort through all of that. And then tomorrow we'll do stereochemistry if you create chirality centers. But the only thing we're going to have time for today is the diene and one of the requirements for it. It has to be able to twist into an S-cis configuration. What is that? Yeah, I knew you were asking that. That's okay. You have a single bond here, which means that rotation can occur. So, and it can come apart. Who knew? All right. So if you have a single bond here, then you can have rotation. And so these double bonds could face on the same side of the plane running through here or on opposite sides. It's a temporary thing, no matter which way it is, because rotation is allowed. And so instead of calling this cis or trans, where it's locked into a particular configuration, you have S in front of it, meaning it's a single bond, so it's temporary, but if you have the dienes on the same side of the bond, of the single bond, then it's S cis, they're same. And this would be S trans if they're opposite like that. Okay? So why does it have to be able to get into this configuration for it to work in a Diels-Alder reaction?
Make a ring the other way.
Yeah, this is not going to close into a ring, right? So it has to be able to get into this configuration. Because if you have your dienophile over here, you have to be able to close the ring that way. Now you might say, well, okay, then what's the big deal? If it's a single bond, it can twist. Not always, always, always. For example, if you had this. If one of the double bonds is already in a ring itself, a ring doesn't allow bond rotation. So if this right here, if that single bond you need to rotate around is part of a ring, then it is what it is. So if it's trans like that, it's locked into configuration. If it's locked into an S-cis configuration, that's extra good because it means that you don't have to work to get it into that arrangement. And so that will be extra great as a reactant. It's just if it's locked into an S-trans configuration, you can't use it. All right, we'll work with it tomorrow.